Till now, we have been looking at spring mass systems kept horizontally on a table. So now let us look at spring mass systems hanging vertically from the ceiling. So the question says, find the time period for the arrangement, for the following arrangement. So in this, we have a spring mass system suspended vertically, spring constant K, and mass of the block is M. So we need to find out the time period in such a situation. Let us start solving this question. So before attaching the mass, let us assume that the spring is hanging vertically. So we have not yet attached the mass to it. In this situation, the equilibrium length of the spring is going to be L, where L is the length of the spring hanging vertically. Now notice that in this case we are considering massless springs, so the spring does not have a mass of its own. So this is the equilibrium length, the length of the spring, and it is suspended vertically. Now let us attach the mass to it. Let us attach the mass to it. So attaching the mass to it would lead to some elongation in the spring. So our equilibrium position would change. So if this was the original equilibrium position, now there is a certain displacement due to the addition of the mass. This is not the displacement that I am giving to the mass. This is at equilibrium, where everything is stationary, nothing is moving. The displacement x that we provide to the mass is afterwards that would cause the simple harmonic motion. Right now everything is stationary. This is the equilibrium position. This is also equilibrium position. But after the mass is attached, so in such a situation we have some displacement, let us call it y naught, some extension in the spring as a result of attaching the mass to it. So since this is a situation of equilibrium, that is the net force acting on the mass is 0 and this is all stationary. So equilibrium meaning net force is 0 and this is all stationary. So in this equilibrium situation, net force is 0. So what are the forces acting on this block? So let us draw the forces acting on this block. So we have mg acting downwards and we have restoring force due to the spring acting upwards. So this is the force due to the spring, this is the restoring force. So the net force on the block, so total force on the block should be equal to 0 in equilibrium. So this gives us, notice that mg and restoring force are in opposite directions. So we have mg minus Fr, the restoring force, equal to 0, and the restoring force by Hooke's law, the restoring force is nothing but minus kx. So the restoring force, but notice that we have drawn these vectors in their proper directions. So mg is acting downwards, restoring force is acting upwards. So restoring force is acting upwards, that takes care of the negative sign in the Hooke's law. So we have over here simply k times the extension, which is y naught. This is coming from Hooke's law. Which says that the restoring force is equal to negative k times displacement. This negative sign basically shows the direction in which the force is being applied. So we have already drawn this vector opposite to mg, so that negative sign has already been catered to. This negative sign simply means that the force is opposite to the extension. That means restoring force is opposite to extension. This comes from this negative sign right here. So we get the expression for y naught. Y naught is nothing but mg over k. So this is the extension for equilibrium. Remember that we have still not displaced the block by some x displacement. This is still all in equilibrium, and this is still, everything is stationary over here. Now we will displace the block by x distance, or rather we are calling this the y direction, so we will displace by y. This direction over here is the y direction, so we will displace by some y displacement. So if I redraw the spring, so I have the spring over here once again. So let me get my pen. So this was the equilibrium length of the spring. This was the displacement caused by adding the mass, which led to a new equilibrium position. And from this position, we will further displace the block by some y distance. So this is the displacement that we typically talk about in simple harmonic motion. So let us now look at the forces. So Fr and mg were counterbalancing each other. So this new displacement y is going to cause the restoring force. So from this y we have the net force acting on the block is minus k times y, again coming from Hooke's law. So Frmg balanced out, but still we have the net force, the net restoring force as minus ky. So this is net restoring force after equilibrium due to displacement y. So now force is nothing but mass times acceleration. So we have the following. Rearranging gives us so this is the equation of SHM. This equation right here signifies that we have SHM motion, and the frequency of this SHM motion is given by, rather the angular frequency is given by square root k by m. So this term right here is omega squared, k by m is omega squared. So this is the governing equation for SHM. And now since we have found omega, we know that time period by definition is 2 pi over omega, which gives us 2 pi square root m over k. So this is the solution to the problem. We have found out the time period. Now from this equation out here, we know that m by k is nothing but y naught by g. So we can rewrite it in another form as follows from this equilibrium equation out here. Notice that this time period 2 pi root m by k is the same as that for a horizontal spring mass system. So a horizontal spring mass system on a table being displaced by x distance also gives us the same time period. Even in this case, we have the time period 2 pi square root m over k. So what do we conclude from here? We conclude that a horizontal spring mass system is essentially equivalent to a vertical spring mass system. There is no difference in the time periods. What is the only difference between this horizontal and vertical? That is the equilibrium position. So in horizontal spring mass system, the equilibrium position is the same as the natural length of the spring There is no extension in the spring in the case of horizontal spring mass system in the equilibrium situation, but in the vertical situation, the equilibrium position itself has some extension in the spring. So this is not the natural length of the spring. But other than that, the time period for both of these is going to be the same. So, the horizontal spring mass system is essentially equivalent to a vertical spring mass system. Only difference is that in horizontal spring mass system and in the vertical spring mass system, the equilibrium positions are slightly different. In the vertical, even in the case of equilibrium, we have some extension in the spring, but in the horizontal, in the equilibrium position, we have no extension in the spring. So here we see in the vertical case, we had this extension in the spring y naught, which was the equilibrium position after the mass was attached.